Here's another example that looks really scary, but it's not, because look at each part of the function. So if you look at arctangent, if we let u equal arctangent x, we need to find the differential. Then du is the derivative of arctangent, which is 1 over x squared plus 1 times dx. But look what those other parts of our integral are. So that's perfect. So really, I can put this in terms of u. I have the integral of u squared, and then this dx over x squared plus 1 is just my du. So this is simply this u cubed over 3 plus c, and then I put it back in terms of x. And I get 1/3 arctangent cubed plus c. Here's another example. It's a little more complicated. So again, we've had good luck with whenever we have an inside function letting that be u. So let's try that. So if we let u equal x squared plus 1, then how do we find du? Du is 2x dx, right? So then I would have u to the 1/2 replaces the square root. I have 2x dx is equal to du, which means 1/2 du is equal to x dx. But I have x cubed dx here. I don't have x dx only. So I need to do a little more work. So we have that factor of x cubed. So again, look back at what you said was u. So if we solve this for x, we get x squared equals u minus 1. And that works out because I have this factor of x here from my expression for du. And then since x times x squared is x cubed, I can replace that x squared with u minus 1. X cubed dx is going to be u minus 1 times du over 2. And then the square root of x squared plus 1 is going to be simply square root of u. So I can turn that into the integral of sums of powers and use the power rule on each of those. And then putting it back in terms of x, this is my solution. So up to now we've just been looking at indefinite integrals. So you can also use the substitution rule for definite integrals, and obviously because you have the same process up until you evaluate it at the limits of integration. But one thing that you can do is, if you want, since a definite integral evaluates to a number, you can evaluate your the antiderivative in terms of u. You can evaluate it at the inside function, evaluate it at your original limits of integration. So it's easier to just show an example. So here I have sine of t over cosine squared t, and my limits of integration are 0 and pi over 6. So again, I can recognize that I have a composite function here of cosine squared t, and the if I let u be cosine t, then du is sine t dt. Excuse me, minus sine t dt. So I know that my substitution is going to be u equals cosine t. So then du is minus sine t dt. And then what I can do is change these limits of integration to be in terms of u as well. So when t is pi over 6, I'm going to evaluate my new, using my substitution to get a new limit of integration. So then u equals cosine pi over 6, which is the square root of 3 over 2. So I'm going to replace this upper limit with square root of 3 over 2. And likewise, I'm going to take that lower limit and I'm going to put that into my substitution. And the cosine of 0 is 1. So I'm going to replace this limit, the lower limit, with 1. So here's my original integral, definite integral. Here I'm replacing everything with in terms of u, including the limits of integration. So notice that, remember that the negative definite integral from a to b is equal to the definite integral from b to a. So I'm just getting rid of that negative sign and adding upper and lower limit of integration. So this is u to the minus second du. I find the antiderivative and I evaluate it at these new limits of integration that I've gotten from my substitution. So at this point, we could have substituted back so that our antiderivative was minus 1 over cosine t, and then evaluated at the original limits. But that's an extra step that you don't really need to do. Oftentimes it's easier to just find the new limits of integration and evaluate your antiderivative in terms of u.